Okay, thank you very much. I'd like to thank the organizers for this opportunity. And like the other lectures in this summer school, this is going to be about certain kind of imperfect cognition. The imperfection will be imperfect ability to perceive causal relations. And like many of the other lectures, it's going to be about, to some extent, some intersection with AI and statistics. It's going to be a different kind of AI, a different kind of statistics. Let's zoom out a little bit and define a certain benchmark. And the benchmark is standard equilibrium analysis in economics. And standard equilibrium analysis in economics takes a steady state approach. That is, we're looking at some stationary distribution. Even in a dynamic model, we will be looking very often at some kind of Markovian process. Within this steady state, individuals best reply to their beliefs. And those beliefs reflect a perfect understanding of the regularities of the steady state. Now, there is a research program in the last few decades that takes those two components, keeps them, continues to assume individual rationality, continues to use the steady state approach rather than a dynamic learning approach, but relaxes the assumption that agents understand the steady state. So write some model in which there is some kind of systematic misunderstanding of the regularities of the steady state. But when you think about what does it mean to misperceive the regularities of the steady state, to some extent is misperceiving the causal relations among relevant variables. One of the variables is your action, another one is some information that you observe. There are lots of other variables, some latent variables perhaps, there are some outcome variables, some intermediate variables. There is a causal web of relations between those variables, and to fully understand the steady state, you need to fully understand those causal relations, and you need to be able to quantify those causal relations through observational data. That is what you learn by being exposed to the steady state. And so if we want to relax the assumption that agents fully understand this steady state regularities, maybe one approach to thinking about that is to have some kind of behavioral approach to causal reasoning. Not a normative approach, the thing that you imbibe during your econometrics classes, but a more behavioral approach. I mean, not how econometricians should do causal reasoning, but how humans do causal reasoning as part of their economic decision making. So this is what this research program is about. So in these two lectures, I'll try to give you some intro into a framework for equilibrium modeling. And I use the term equilibrium modeling, even though you'll see that most of the time I'll be talking about single agent problems. So the equilibrium perspective will be relevant, even though we'll be looking not at games or markets, but just a single agent problem, but still the equilibrium perspective will be fundamental. So it's going to be a framework for equilibrium modeling when agents exhibit some kind of imperfect causal reasoning, mainly misunderstanding the causal relations in their environment. A building block of this modeling approach is going to be the tool of directed acyclic graphs, DAGs, which I borrow from the AI statistics literature on probabilistic graphical models, specifically the class of graphical models that are known as Bayesian networks. And those directed acyclic graphs are a very convenient tool for representing subjective causal models, and you can use them to represent also misperceptions of causal relations. So I'll show you this kind of approach, how to use it to write down models of decision making when people don't understand causal relations. Now, with something like that, there's always going to be some kind of mix of tools that enable you to build a model, build an economic application, and analyze it. But these can also be tools that help you prove theorems about general classes of models. I'll do mostly the former rather than the latter, given the time constraints. So I'll mostly try to show you how you can use this approach to write down. These are going to be very stylized toy economic applications, but still it's going to be geared toward writing down models and analyzing them. And these are the examples that I'm going to cover in this lecture. There's more, but I won't have time. So I'll start with an example about lifestyle decision making. The end of the first lecture, maybe spilling over the next lecture, I'm talking about a little example of demand for education, and in the second lecture, I'll be talking about political narratives. The sources for this lecture, well, my own work. This is a review article. It could be a good entry point. The specific examples that I'm going to present today, or the results I'm going to present today, I'm going to be taking from 3 specific papers. If you want to learn more about Bayesian networks, this is not going to be a primer on Bayesian networks, because as I said, I'm mainly going to use it to show you how you can use the language to build models rather than using results from the literature to get general theorems. But there are interesting things. It's a nice, very nice literature that I enjoyed learning. These are a few textbooks emphasizing different aspects. Some are more probabilistic, some are more computer sciencey. This is a popular book, Pearl and Mackenzie. This is a popular book called The Book of Why. It's good entry into this approach. Within economic theory, the closest works to what I present today are recent, not entirely recent, approaches to equilibrium modeling with non-rational expectations. There's Philippe Gilliel's analogy-based expectations equilibrium. There's Esponda and Puzo's notion of Burke-Nash equilibrium. I won't have time to explain the relations, but there are strong relations between what I'll present today and what these people are doing, and there are other approaches out there. I won't have time to explain fully, but maybe it will come up during the questions, and I'll be able to clarify that. One apology is that I am aware of psychology literature on causal reasoning. I know a few works. I don't know as much as I should have, and I think one direction for thinking more deeply about this problem is learning more psychology. I mean, there's this is just I didn't have a lot of space in the slides, so these are just 2 examples of relevant references. There's a lot more, and I'm aware of that, but I can't really say that I really used a lot of that in this research, but I think a lot can be done in this direction, trying to learn more from psychology of causal reasoning and trying to incorporate that into economics. Here's the lecture plan. So first lecture, I'll start with an introductory example, just to try to, like 20 minutes of trying to show you with an example how you could think about these things, about what does it mean to make a decision when you misperceive causal relations in your environment. Then I'll present more generally the DAG language. I'll integrate it into a decision model, and then I'll give you another example. Again, could be spilling over to the next lecture. In the next lecture, here in the first lecture, I'll be taking the causal misperceptions of the agent as given. In the second lecture, I'll endogenize it. I'll tell stories about how those models, those causal models, can be influenced by others. For example, there could be political parties and spin doctors pitching political narratives and basically battling over public opinion. And so I'll be trying to give you a little model of this kind of battle over public opinion in the form of competing political narratives. And then at the end, I'll switch to a mode that is less about examples and more about general results, and I'll be talking about the maximal distortion of correlations that you could get with misspecified causal models, but I will give it like a persuasion story. So there will be, again, some notion of an endogenous causal models with the idea that there is a persuader who is trying to get you to hold certain beliefs, and one of his instruments is to pitch you a model that could be wrong, but using that wrong model, it could get you to hold certain beliefs that are very far from the truth. So that's the lecture plan. Questions before I start? Okay, so the introductory example is something that I call the dieter's dilemma, and here's the story. And again, I'm only tell you a story. There's an agent who has to decide whether to consume a dietary supplement, and he's going to misperceive some aspect of the causal relations in his environment. And as we go through this example, we'll see the challenges in writing down a model of decision making under this kind of causal misperception. So here's our agent, chooses whether to consume a dietary supplement. And we're going to be 3 binary variables in this story. The action, binary, whether to consume the supplement or not. A equals 1 means that you consume the supplement. Then there is H, representing the final state of your health. 1 means good health and 0 means bad health. Then there's a third variable, C, that is also binary, and that represents the blood level of some chemical in your blood. You can think serotonin, you can think cholesterol, think about those things. And 1 will mean that it's an abnormal level, and 0 means that it's a normal level. So those are the variables in the story. our agent doesn't care about this variable at all. All he cares about is H and A. Consuming the supplement is costly. The cost is K. And he just wants to be in good health, so his payoff is H minus KA. Okay? So the only reason he would pay for the supplement is if he thinks that it's going to improve his health. And now here's the equilibrium perspective. Although it's a single agent problem, I want you to think of this single agent as arriving at the scene after a population of similar agents face the same problem, and they produce the data set. So there is a long-run distribution, long-run or steady-state distribution, joint distribution over these three variables, resulting from the cumulative behavior of other agents facing the same situation. So it's a one-shot decision problem for our agent, but he's taking that decision against the background of some population that face the same problem. So this A is, in this case, is recording the behavior of other agents in the population. Now, the fact of the matter in this example is that your probability of having good health is 50%, independently of what you do. When I say independently, I mean both statistically and causally. No matter what you do, in reality, objectively, the supplement is not going to change your health. You're going to be equally likely to be healthy or unhealthy, independently of what you do. And therefore, if you understood that, certainly you don't really care about this C, so this C is completely irrelevant, and your rational choice, if you understood that causal and statistical regularity, would be to take the action 0, not consuming the supplement because it's costly and it doesn't have any effect on your health, so why bother? So that would be the benchmark with rational expectations. So we already, even without knowing how C is jointly distributed with A and H, we know what a rational person would do, would not consume the supplement. But now I'm introducing the behavior of C as a function of A and H. I'm writing this as a conditional probability, but I want you to think about this causally, that in reality C is a consequence of A and H, and it's deterministic, given by this formula, very simple. Your chemical level is going to be normal if you're either healthy or you take the supplement. Okay? So it's like you're going to have normal cholesterol levels if you don't have some underlying health problem, or if you take statins. Okay? Something like that. I don't want to, I'm using the cholesterol language just because it's familiar. I don't want to suggest that statins are not good for your health. I take statins. So pick your controversial chemical. You will easily find one. I'm not claiming that statin is one of them, or cholesterol is one of them. Okay, so this is the true process. The true process is that your chemical level is normal if you either take the supplement or if you're healthy. But if you're unhealthy and you don't take the supplement, then your chemical level is going to be abnormal. And here we arrive at the misperception. The misperception of the agent is going to be that he believes in a certain subjective causal model, which is very intuitively represented by directed acyclic graphs. These graphs are just like game trees. When you write down a game tree, people understand what it means even without really any need to give some kind of formal mathematical definition. When I write this, you kind of understand what it means. But in any case, I'm going to explain it, of course. The belief is that A causes H through C. So he believes that A has a causal effect on H. And notice this is a qualitative belief. It's not a quantitative belief. You look at the data to quantify this belief, but it's a qualitative belief in causal relations that A causes H through the mediator C, and that there is no other causal channel. So he believes that C is the only direct cause of H, and that A causes C. That's his belief. So that's the first part of the decision model. First, just having this kind of mental representation, this subjective causal model, which we can represent with a directed acyclic graph. And it's a directed acyclic graph because there are 3 nodes, and there are links, and the links are directed, and there are no cycles. Okay? So that's why it's a directed acyclic graph, or rather, it should have been an acyclic directed graph, but somehow DAG sounds, I guess, better than ADEG, so this name stuck. So it's a DAG. That's the first part. So he has this causal model. How does he arrive at a quantitative belief? Well, he fits the causal model to the data. What does it mean to fit the causal model to the data? I'm just going to write down a formula now, and I'm going to present the general formula later, but it's kind of intuitive in the sense that if if the model were indeed consistent with the data, it would be possible to write down the joint distribution over A, H, and C this way. That first A is realized somehow, because you draw a person from the population plays some kind of mixed strategy perhaps. So you draw a person from the population, they take A causes C, so C is some probabilistic function of A, and then H is a probabilistic function of C, but just of C. It's not a function of A, because C is the only direct cause of H. So if the true data generating process were consistent with this causal scheme, then it would be possible to write down this joint distribution over the few variables in this factorization form. So for now, I'm just going to just write it down like this, as like a definition for this example, that this is what it means for the agent to fit his causal model to the data.
But the true data generating process, you can also write this way, right?
No, I'll get to there in like 2-3 slides. No, the true data generating process is going to be, this is a wrong factorization that can lead to a mistake. And I'll explain that in the next.
That H is probability of H is a half conditional.
I'll explain that in the next few slides. But there is a mistake. Given the true data generating process, this is a wrong factorization. And I call this P sub R of AHC because it's the distribution, the P comes from the actual data generating process, and the R is the subjective model. So it's fitting the model R to the data P, and you're estimating the model, you're imposing the model on the data, and I call it P sub R. It's the model, it's the distribution filtered through the prism of the subjective model, and in general this will be different from the true joint distribution. You'll see that in a second. Yeah.
A determines C.
That's what you believe, it's not the truth. A determines C.
No, I understand that it's not the truth, but then you should expect to see, you know, that C is determined by A.
Yeah. This is
So
what
why
it says. It says P determined by
C given A, probably, I mean, it's determined by A.
The,
What's the probability?
No, when I say determined, I mean determined probabilistically. So this thing doesn't mean that the truth is deterministic. It's a qualitative scheme, but those relations are those relations are probabilistic, and to arrive at these probabilities, you estimate that through the data.
So this is not a deterministic.
It's not a deterministic. This is just a qualitative scheme of the causal perception, where you don't have any prior about the strength of this link, the magnitude of this link, the noisiness of this link, but you are sure that there is no direct link from A to H. Okay. So effectively, statistically what you're really imposing here, and this will be partly half the answer to those questions, you're actually assuming that A and H are independent conditional on C. And that's going to be the wrong thing that you're imposing on the data. So the agent is going to rely on this subjective belief, which again, he uses the actual data, that's the population statistics. He uses the population statistics to estimate this belief. And he uses that also to compute the indirect effect of A on H. And he does that intuitively, right? Because you think that A affects H through the channel that goes through C. So you sum over the possible realizations of C, and for each one of them you calculate the probability of C conditional on A, and then the probability of H conditional on C. This is what you would do if you thought that A causes C via H. But of course the agent could have just looked at the data, because if he has the data on the joint distribution, if he has access to the population statistics about A, C, and H, you could just look at the correlation between A and H and directly estimate that correlation. And by the way, if you looked at that, you would actually see zero correlation, because these things are independent. So why isn't he doing that? 3 answers. Maybe there are more, but I'll give you 3 answers. One answer is something that can be formalized, and this is the connection to Burke-Nash equilibrium, actually. You could think of that in terms of Bayesian learning. You arrive at the model, you arrive at the scene, before observing the data from the other people's behavior. You arrive with a dogmatic prior that the causal model is correct, in particular that A and H are independent conditional on C. And then you interpret the data and you update your beliefs with this dogmatic prior. The long-run belief, you can show that the long-run belief of this updating process is going to be given by this formula. So this is going to be the Bayesian long-run belief if you have this dogmatic belief that A and C are A and H are independent conditional on C. That's one answer, just Bayesian learning. The other answer is that we're economists, so we know that people use models that are wrong, and we use models to interpret things. And the reason we do that is, again, to economize. It's not like each time you have a quantitative question, you're going to look at the data and estimate the relations that you're interested in from scratch. You will have a model, you will estimate it in some sense once and for all, and then you'll use that model to answer a bunch of questions about conditional probabilities. Those conditional probabilities could answer diagnostic questions, they could answer questions about interventions, but this idea that you use models, estimate them, and then use the same model to answer a bunch of questions, the estimated model to answer a bunch of questions, rather than looking into the data each time you want to answer a quantitative question, we're familiar with that idea because we have friends who work at central banks. And so you should think, one way to think about this model is along similar lines, that the agent works with a model, estimates the model, and then uses that model to answer a bunch of questions he's interested in. Finally, I said if the agent has access to the data on A, C, and H, but maybe processing that data or accessing that data is costly. So if I believe that A, C, and H are related via this causal chain, all I need to look at and process is I need to hire my RA, so to speak, to run two regressions, to regress C on A and to regress H on C. Maybe the data on A and H is much harder to come by. Maybe it's less accessible. So one interpretation of what's going on here is that maybe different data have different difficulty of accessing or processing, which is why you end up computing this thing rather than computing this thing. My point is that this is an important question, needs answering, so I've given you 3 ways of dealing with this critique, but it is still an important critique. Why do people rely on models to form conditional probabilities rather than estimating them directly from the data? It is a question, it is a critique, these are answers, but it's not like critique proof. It is a problematic aspect of the model. Okay, so this is the agent's conditional probability of being in good health conditional on his actions. What is the mistake? Remember that this, as I said before, this belief, from a statistical point of view, it means that the agent thinks that H and A are independent conditional on C. That's the probabilistic meaning of this causal assumption. But this assumption is false given the true data generating process that I told you. Remember what I told you the true data generating process is about. You have this chemical level which is normal if you take the supplement or if you're healthy. Yes, if you take the supplement or if you're healthy. If at least one of these things holds. But suppose, so what would it mean for H and A to be independent conditional on C? It means that, suppose that I observe your chemical level. If I now learned what your A is, would I update my beliefs about H? If this is true, then I wouldn't. So given C, if you also told me now A, I wouldn't update my beliefs on H. But that is not true given the true process. Because suppose that I see somebody and I measure the chemical level and I see that the chemical level is normal. Now this person is telling me, by the way, I don't take the supplement. Then I will say, well, then you must be healthy. Given the data generating process that I told you, you only have normal chemical level if you take the supplement or if you're healthy. At least one of these 2 things has to be true. So if I see that you don't take the supplement, I must conclude that you're healthy. In other words, this conditional independence property that you assume, that your causal model assumes, is wrong. So that's one way of seeing what the misspecification is in terms of a wrong conditional independence assumption that the agent assumes when he interprets data. A different way of seeing the mistake that the agent is making, and this is answering Tomas's question, this is a true factorization of the true process, because A and H are realized independently, and C is a function of A and H. So this is a true factorization, a correct factorization of the true data generating process. And notice that this is consistent with this DAG. Like A and H don't have any causes, and C is and they're independent, and C is a consequence of those two causes. So this is the true causal model underlying the data generating process. This is the subjective causal model. And you can see what the difference is. The difference is that the link between C and H is inverted. In other words, our decision making is exhibiting reverse causality. So he's reversing the true causal relation between C and H. In reality, C is a consequence of H, but he thinks that C is a cause of H. So from a causal point of view, his mistake is reverse causality. From a probabilistic point of view, his mistake is that he's assuming a wrong conditional dependence assumption when he interprets the data. Okay, so that's the misperception. Now let's move to decision making. How will our decision maker choose A? Well, this is what he's calculating, right? Because this is his utility, H minus Ka, and this is his perceived probability of the effect of A on H. So effectively, he's asking himself, if I take the action A, what's going to be the probability of good health? And you subtract that from that the cost of taking the action A. And remember that this object here is elaborated into this factorization. Now notice this term here. What is this term here? That's the probability of being in good health conditional on C. The decision maker proceeds and he estimates that from the data. Now we're not the decision maker, we're the analyst. We want to know what he's going to do. He can calculate that because he looks at the data and calculate that. We can't calculate that for the following reason. Remember, H is not independent of A conditional on C. So if we don't know the distribution over A in the population, we can't calculate that. You'll see that in a second when I write down explicit formulas. You'll see that without knowing what the distribution of A in population is, we can't actually unambiguously calculate this. This conditional probability, and therefore this conditional probability, is not invariant to the population level distribution over actions. In other words, even though we're looking at the single agent decision problem, we actually we're led to analyzing it, defining it as an equilibrium phenomenon. Because to quantify the decision maker's subjective expected utility, we need to know what people in the population are doing. So this suggests a natural equilibrium concept, which I'll write it down like this. In equilibrium, if an action is taken with positive frequency, then it must be a subjective maximizer, and that will be in equilibrium. Yes?
I have a basic kind of confusion that I should have asked much earlier. Suppose there's just two variables, then I could say A causes B or B causes A. These mean different things to me, but it seems to me that they mean the same thing to you.
It's not confusion. You're actually thinking like 10 slides ahead.
But that's very confusing.
Yes, but don't allow yourself to be confused by that. It's not going to be an issue. Okay. I'll clarify that. It's more confusing. How can I alleviate your confusion without skipping 10 slides ahead?
That's fine. I can remember.
There will be. Let's
go
go to some kind of mutual confusion session. It will be a lot of fun. It is true. The misperception, that's why I emphasized, when I talked about these things, I emphasized two levels of the misperception. The causal misperception, that you get the graph wrong, and the probabilistic misperception, that you get the conditional independent structure in the environment wrong. There is a redundancy in the graphical representation. You could have two graphs that represent the same conditional independence properties, but they look different. For example, 1 causes 2 or 2 causes 1. And they're going to be equivalent in terms of the conditional independence assumptions that they impose. So you're not confused. It's true. It's not that I'm saying that every deviation of the subjective causal model from the true causal model is going to lead to a mistake.
Okay, so these graphs only represent some conditional independence assumptions. There's really nothing about causality there, or?
This is where it becomes confusing. But no, because the agent is going to the agent is calculating this thing. When you write down an expected utility model, decision making on games. Why do you write that? We do this all the time. We do this like 8 hours a day. I've been doing this for 20 years now, and I do this all the time. What do I mean by when I do that? Obviously, I mean a causal thing. I'm not just calculating a conditional probability. I give it a causal interpretation. If I take this action, given the signal, actually usually there's also a signal. I observe a signal, I take an action, and then there's an outcome. So I actually calculate the probability of the outcome conditional on the action, the signal. What I mean is that the action is meant as an intervention, and the signal is just given the signal, right? So I'm given the signal, what's going to be the causal effect of my action? But you just write a conditional probability formula. The conditional probability formula doesn't know that when you condition on the signal, it's just conditioning, and when you're conditioning on the action, it's intervention. That's one of the things that Pearl emphasizes, that our notation sucks in many cases. Regression equations, conditional probabilities, our notation sucks in terms of understanding the causal meaning of conditional probabilities, and that's why he invented his own notation. That's part of the confusion. But in reality, what you're doing here is that you really are calculating. The decision maker, true, he's just looking at conditional probability, but he imposes a causal interpretation on that conditional probability. So by doing that, he's basically taking this one causes 2 and 2 causes 1, and he insists on a particular causal interpretation, even though for certain calculations, the only thing that matters is just the conditional probabilities. The point is that it's confusing, but for everything that I do today, it's not going to matter. There's a new paper of mine that I call behavioral causal inference when I tackle this kind of thing head on, but for everything that I do today, it actually won't be confusing. It may be confusing, but don't worry about it. So that's the answer to confusion. Don't worry about it.
But this is related to the fact that decomposition in several factors is not unique.
Yes, and I'll talk about that. Exactly. That's exactly. It's just saying it in different words. Yeah.
I just want to make sure I understand why you need an equilibrium concept. Just to justify the idea that you're in a steady state.
It's even more basic than that, I think. I think that the point is that if I want to describe how the decision maker makes a decision, the decision maker knows this thing because he looks at this population, but we don't know this. We're the analysts. I don't know this unless I know what the distribution over actions is in the population, because again, this thing is not independent of A according to the true process. So I'm not saying that the only way to resolve that is through an equilibrium concept, but the natural, for us as economists, the natural way of resolving that is through an equilibrium, to have a distribution over actions such that the actions that are taken are subjectively optimal given the distribution of actions in the population. So it suggests a need for equilibrium. It doesn't force you to write it down as an equilibrium. But the point is that you just, without knowing what the people in the population do, you just won't be able to calculate that. I'll write an explicit formula in a second, and you'll see that you just, without knowing that, you can't actually calculate this. There's going to be a missing term that you just need to plug into the formula in order to actually calculate it and know, therefore, what the decision maker is going to do. No, I didn't answer your question.
Well, you have the same data that the decision maker has, right? You know the joint distribution.
Yeah, all I'm saying is that without knowing the marginal over A, I can't calculate this. That's all I'm saying. I'm sorry?
If you have the joint distribution.
Yeah, but that is that. But yeah, of course. But one of the things that are going to be in there is the marginal over A. That's all I'm saying. For different marginals over A.
Analysts can know what would be the probability.
For different marginals, let me put it differently. For different marginals over A, you will get a different answer.
No, but the marginal over A is fixed. If you have the joint, you have the marginal.
Yeah. For different.
So this is a number.
It's a number that where the prediction of what the agent is going to do depends on the marginal. That's all I'm saying. The decision of what the agent is going to... In a single agent decision problem, in the standard model, your decision is not independent of what many people in the population do. It's not. It's not a game. It's a decision problem. Here, in a single agent decision problem, the optimal decision for you depends on the distribution of actions in the population.
Right.
But you know that distribution, right? If you know the joint, you know the marginal.
Yeah.
So
Yeah.
why do you need equilibrium?
This suggests that an appropriate way to analyze what's going on here is an equilibrium.
I can understand for you to believe that this is a steady state, then
Sure. Okay.
an equilibrium would justify that.
Yeah.
But if you don't care about steady state,
Then you don't have to. Then you don't have to. Yeah, absolutely. Okay. But then you'll have a free parameter in your model which says, depending on what other people in the population do, this is your prediction. It's not a cool theory of decision making. You could say the same thing about games, right? So tell me what the others are doing, I'll tell you what you're doing. It's not a great prediction of what's going to happen in the system. So personal equilibrium, I'm snatching the term from Koshegi and Rabin, but in a different context. If an action is taken with positive frequency, then it's a maximizer, given the subjective belief. This is not precise. I need to introduce trembles in order to make this precise. I'll do that later. But let's look at the personal equilibrium with full support, such that both actions are taken with positive probability, so that we don't have to think about trembles. And if both actions are taken with positive probability, then they're both maximizers. That means that the subjective benefit from taking the drug is equal to the cost. So that's the willingness to pay of the decision maker for the drug. It's his perceived probability of being in good health when he takes the drug, the supplement, minus the perceived probability of being in good health when he doesn't take the supplement. And that perceived benefit should be equal to K. That is how both act. It's just like in mixed strategy, Nash equilibrium. It's just, again, but it's not a game. It's a decision problem. So it's going to be indifferent between these two things. So that's our equilibrium condition. And remember, again, that these two quantities here are given by these terms. Each of these terms is something that you can calculate from the empirical distribution. So let's do that. Let's just calculate these things. I'm reminding you, H equals 1 is good health, and C equals 0 is normal chemical level. These are the relevant terms that you need to calculate. So let's just go over a few of them, not all of them. For example, the probability of having a normal chemical level when you take the supplement is 1. We assume that. We assume exogenously that if you take the supplement, you're going to have a normal chemical level. So that's 1. This is 0 because when you have an abnormal chemical level, it must be that you're in bad health. Otherwise, you would have a normal chemical level. That's why there's a 0 here. This is where you actually see the endogeneity aspect. What's the probability of being in good health when I see that you have a normal chemical level? Well, it could be for two reasons. Maybe you took the drug, or maybe you're healthy. So this is the Bayesian update. But to calculate that, I need to know how many people in the population take the drug. So this is where, to calculate this thing, we need to know this thing. So this is this endogeneity thing that I mentioned, that you wouldn't have this problem if the causal model were correctly specified. If the model were correctly specified, you wouldn't have those kind of endogenous things popping up here on the right-hand side. So you plug these terms in the equilibrium condition, you get this equation. And that's the equilibrium solution. There will be an equilibrium, and it's going to be unique where both actions are taken with positive probability only when K is between 1/4 and 1/2. If K is outside this interval, then you're only going to have a pure equilibrium sustained by tremble. So I'm not going to talk about that. But the point is, of all this exercise, what did we do actually? I took you through a journey of saying, okay, there's this story of this person who wants to, considering taking a supplement, he just have a wrong causal perception that he thinks that the chemical level, that the supplement will affect the chemical level, and he thinks that the chemical level is a cause of the health outcome, whereas in fact it's the other way around. The chemical level is a consequence of the health, of his health state, and what does it mean to make a decision in under such a misperception? So first we saw that there is this endogeneity aspect, where again I don't have to analyze it as an equilibrium phenomenon, but it's natural for an economist coming from game theory to think about this as an equilibrium object. So we wrote it down as an equilibrium concept, and we saw that actually we do get an unmistakable equilibrium aspect here, which is the mixing. The unique equilibrium with mixing, that's not something that you would get from a standard expected utility maximization. there is an unmistakable equilibrium aspect to that. So that was the point of this example.
Yes, that might be a stupid question. Why do you call this personal equilibrium instead of misperception equilibrium?
I use the term personal equilibrium just to emphasize that it's in a single agent decision problem. It's a single agent decision problem, and nevertheless I analyze it as an equilibrium phenomenon. So, and again, I borrowed the term from Pasheg and Rabian in a very different context. I think it's a good term in the sense that it emphasizes that although it's a single agent decision problem, you use an equilibrium. Now, here I should say that this observation that an equilibrium methodology is a good or potentially relevant way of analyzing behavior under misspecified models, I'm not the first person to notice that. There's an old example by Nyarko, in the context of some monopoly pricing example, and it popped up in the literature in various cases, but with this modeling approach and with Esponda and Puzo, Burke-Nash, I think we have a better understanding of this equilibrium aspect of decision making under misspecified models. Here, the misspecification is causal.
So the motivation for the misspecification is that it's easier to learn from data, is that correct?
That would be one interpretation,
Okay.
but not the only interpretation. It could be really some kind of Bayesian dogmatic conviction of a certain causal mechanism. We just get it wrong. There are these two interpretations. Yes.
So in the framework along here, it can only impose dependencies which are not in the data, but cannot do the reverse. I mean,
If you do the reverse, then it's kind of trivial. If you just relax conditional dependence assumptions that exist in the data, you're not going to make any mistake. That's going to be a feature of the model. It wouldn't be the case if you had a finite sample, but here there's going to be implicitly an infinite sample. So believing in dependencies that don't actually exist in the data, that will generate mistakes. If you have a finite sample, in fact, the Osborne-Rubinstein SK equilibrium can be viewed in these terms, that imagining that there is a certain dependence or causal effect, whereas in fact there is no causal effect, and because of finite samples, you might get a wrong belief. What I'll do here today works with an infinite sample effectively.
So, for instance, stereotypes, I cannot accommodate stereotypes here. Maybe.
You could with a finite sample. So taking my approach today and on top of that having a finite sample would enable you to get things like that, but not today. No.
I'm also a bit confused. But I suppose to Thomas,
We still have 2.5 hours, you know.
So how do you think of this steady state? Do you think about the population of
A dynamic process where there is a population,
there's
people.
a population, they all have this one model.
I think of this as like a dynamic story where you make a one-shot decision, lots of people took actions before you, you look at their statistics, using their statistics to learn.
But you actually need to assume that everyone in this population has this one model, right?
Yeah. Again, I could extend the model, which I did, and have some kind of heterogeneity in the models. Maybe some of them are rational. You could do that as well. But yes, I'm thinking about a dynamic process, again, an equilibrating process, which would typically be a dynamic story. There have been people in the past who took decisions. I have the database. I impose my incorrect model on that statistics in the database. I take a decision. Then I become a new data point that somebody will come after me and the subsequent player will also have my data point. And this is a process of learning. It may or may not converge. In this case, this process will converge. So we should, I think about this in terms of a underlying dynamic story. So you're not confused at all. I think that's the interpretation. I think that would be my story. I wouldn't tell a story about a single agent making the same decision over and over again. I don't want to do that. So I want to think about lots of people who make one-shot decisions and they just consult data about what other people did. Okay?
In the learning perspective, there's a trade-off between learning a more complicated model and then being less certain about it, or learning a wrong but simpler model and being certain. So there should be some a priori way to know which one is better. You could quantify this.
Yes, but today I'm going to take the model as given. But that's certainly an obvious area for extension. Okay, so that was the introductory example. And let's now present the framework more generally. So let's start with the notion of Bayesian networks before talking about, so what I'll do now, I'll present the notion of the DAG representation and of beliefs. And then at some point I'll introduce the decision model. So here's the DAG representation. Here's the primitives. There's some collection of variables from 0 through n. And there's an objective long-run probability distribution. That's like the steady state distribution over these variables. And for now, I'm not attaching any interpretation to these variables. Actions, consequences, signals, just abstract variables. We know from first lesson of probability that you can factorize P according to the chain rule. So we're familiar with the idea that the joint probability distribution can be written as a factorization formula where the terms are conditional probabilities. So let's take that as, and we also know that there is this, again, multiple ways of ordering the variables. The order in which we enumerate the variables is irrelevant for the standard chain rule. The next primitive is the notion of a directed acyclic graph. So it's a set of nodes and a set of edges. The nodes will represent variables. So it's going to be some subset of the set of variables. So each node will correspond to one of the variables. And R is a set of directed links. So I'm going to use these two things interchangeably. And actually my favorite notation, maybe it's a bad notation, I'm not sure, but I like it. I'm going to call R of I, it's just the set of parents of node I, direct parents of node I. And throughout I'm going to suppress N and just focus on R as the representation of the DAG. So the representation of the DAG is for each of the variables in N, who are the parents of each node. So that was the primitive of the DAG. Now the factorization formula. What is the factorization formula? What does it mean for factorizing P according to a graph? You just go over each of the nodes in your graph, and for each one of them, consulting the P, because you have P in the background, consulting P, you just calculate the probability of xi. For each of the nodes I, you calculate the probability of xi conditional on the parents, which are the perceived direct causes. If we have a causal interpretation of the DAG, I should have said this, if we have a causal interpretation of the DAG where the directed link, the link means a perceived causal effect. So you think if there is a link from J into I, this represents a belief that J is a direct cause of I. Okay. The absence of a link means that you think that if there is no direct link from J into I, that means that you believe that J is not a direct cause of I. Okay, so that's the causal interpretation. And the factorization formula is therefore intuitive in terms of the causal interpretation of this thing. You calculate here the behavior of xi conditional on its direct causes. So for example, if this is your DAG, then this is what the factorization formula is going to look like. 1 and 2, you can see that they're ancestral nodes. They don't have any causes, so you don't condition them on anything. 0 has a single parent, which is 1, so you condition x0 on x1. And 3 has 2 parents, 0 and 2, so you condition x3 on those 2 things. So that's the factorization formula. And it's different from the chain rule in the sense that there's some conditioning that is missing here, because you think with your DAG that you've exhausted all the dependencies. Now, if you had a fully connected DAG, it's like you're not assuming any conditional dependence. You're just completely agnostic about conditional dependence. And so this factorization formula boils down to the chain rule. If your DAG is empty, it's like you think that nothing is connected to anything else, then all this factorization boils down to is just the product of the marginals. You just get the marginals, and you just think that they're not related. So this factorization formula is just a product of marginals. So this factorization formula can be viewed as a generalization of the chain rule, where instead of having a factorization formula that is complete, you factorize it according to the DAG, in the sense that some of these things on the right hand side of the conditioning are missing. So that's the formula. Yes.
We often hear that correlation does not imply causation. How does that relate to your thing here?
I think it's related to your earlier question. So, for now, indeed, the causal interpretation is just an interpretation, and you don't have to buy it. It's just a representation, and this R can just be a device for representing conditional dependence properties. Nevertheless, it's intuitive because of the directionality and the acyclicity. It's suggestive of a causal interpretation because our intuitions about causal relations is that they're asymmetric and acyclic. But you don't have to take that interpretation. And the only place where we will commit to that interpretation is when we integrate this in the decision model. But before we get into the decision model, we don't have to insist on the causal interpretation. And again, it's the same question that you asked before, and it's a good question, and I'm going to go back to that later on. Now, it's one nice thing about this factorization formula is that itself is a well-defined probability distribution. It's a probability distribution, so you can use that to calculate, and I call it P sub R because, again, you're using the true P, because each one of these terms is calculated with true data, the actual distribution, but you put these things together in a way that may distort things. One analogy that I like is Picasso cubism. So he draws correct things, but then he puts them together in a way that distorts the reality. So that's what's going on here. You take correct measurements, but you put them together in a way that might distort the reality. So P sub R is reality viewed through the potentially distorting prism of the model R, which means that P sub R may be different from P. But it's a subjective probability distribution. You can use that to calculate marginals, conditionals. For example, when I is an ancestral node, this is the formula for the subjective conditional probability of x minus I conditional on xi. You just take the terms excluding I. It's just this thing, but without the ancestral node that we're looking at. So this is going to be a useful subjective conditional probability. We will say that what is a Bayesian network? It's the DAG and the set of distributions that are consistent with the DAG. That is the set of distributions that can be factorized correctly with this DAG. Now, what do these things do? So one thing that they can do is just representing condition dependence properties. For example, in the Dieter's dilemma, the graph A causes C causes H could be viewed, forget about the term causality, it could just be viewed as a representation of a conditional dependence assumption. And there is a literature on this, in the probability literature on probabilistic graphical models, which just explores this, the graph, the DAGs, as purely as a representation of conditional dependence assumptions. And since some of us like doing analysis with pictures rather than with algebra, it's useful for some of us as a representation. Sometimes, doing algebra with conditional dependence is confusing if you make mistakes, so you can work with graphs and make fewer mistakes. So it's a simplifying calculational device for thinking about the consequences that you can draw from some assumptions about conditional dependence. The reason that this became important in computer science at some point is that in AI is that people realized that you could use that as a platform for efficient probabilistic inference. So suppose that you have a state space with many variables. So if you just try to do Bayesian updating, computationally becomes really hard at some point. However, if you know that, because the state space explodes in the number of variables, however, if at some point, if you know that the distribution, if you're willing to assume that the distribution is consistent with a relatively sparse graph, there are many variables, but the cliques of the graph are relatively small, then you can come up with algorithms that will do the Bayesian updating or other calculations that you want to run, but mainly Bayesian updating. You can do that efficiently. Okay? So that's the thing that made, that's why Perl got the Turing Prize, for example. Basically for understanding how you could use graphs to devise efficient calculational frameworks. And at some point Perl became greedy and he said, wait a second, let's leverage the causal interpretation of the graphical structure of the DAGs and think about that as a platform for algorithmic causal inference. In other words, letting robots do causal inference. Get the Josh Angrists out of business, or the world out of business, and let robots do causal inference. That's the very impressive thing that he did in this book, Causality. So you could take the DAG structure, and then you really take more seriously the causal interpretation. You don't just view the DAG as a representation of condition independence properties. You leverage that causally. I'm not going to do any of what he did here. I'm not going to use that. But that's the history, a very short history of Bayesian networks and what it did in the AI and computer science literature. What does it do for me? Well, for me, as a theorist who thinks about decision making with systematic misperceptions of steady state, what R does is that it encodes a systematic distortion of objective distributions into subjective beliefs. This P sub R is a mapping. Tell me what the objective distribution P, I will tell you what the subjective belief is. It's P sub R given by the factorization. So take the true distribution, put it into this machine of the factorization formula, and it will spit out a subjective belief. One among other things, and that was actually my initial motivation when thinking about these things. I wasn't thinking about Bayesian networks. I didn't know Bayesian networks. I didn't know about DAGs. I didn't know these things. What I was trying to do was generalizing solution concepts like Hurst equilibrium by Eister and Rabin, or GEL's analogy-based expectations, and they came up with this formula that generalized these things. So in some sense, it's a unifying framework. To some extent, it's unifying of alternative, various types of misperceptions that we see in the literature. So what I want to do now is showing you how you could use this language just to capture belief errors or systematic errors that can be viewed as causal misperceptions. Yeah.
So here everything will depend on the DAG that you choose. Right?
Yes. What do you mean by everything?
The
yeah.
results.
Yes.
It will depend on the DAG.
Yeah.
But is there some theory of how people choose this DAG
So
versus another one? They're all approximations of a joint distribution.
It's the usual thing in economics where, you know, for example, in many applications you take people's information as given, and then in another application you endogenize the information acquisition. The same thing here. I'll start in this lecture. I'm going to take this subjective model as given. Now, where is this coming from? How do you know in the context of an application what someone's subjective model is? You can ask the same question about how do you know his preferences, how do you know his information. In principle, you can elicit that, and you could, in principle, elicit this from choice data. So it is something that to some extent can be elicited from choice behavior, but in the context of an application, you just take that as a primitive. And sometimes you may want to endogenize that, like saying that maybe the reason you hold a certain belief is in a causal model is that somebody sold you that, managed to convince you somehow to hold that, to believe in that model. Sorry, there's a question.
Dietary supplements example, the manufacturer might tell you that if you take this,
you can be exposed to those kind of models through the media, through interested parties. That's what I would call, taking a term from Sundaram and Schwarzstein in a different context, using a model to persuade. Yes?
And can they get some strange results? For example, if they use incorrect formulas, they can get the overall probability of everything is less than 1 or greater.
No, it's okay. So to your narrow question, the answer is no, because it's a well-defined probability distribution. But for example, one question is, does it distort marginals? So one of the things that I did in this project, and I'll give you a little taste of that at the end of the second lecture, is trying to get some predictions or analysis of the kind of distortions, trying to understand this P sub R. It distorts some things, but it preserves other things. Trying to get a more systematic understanding of what does it distort, what does it preserve. There is a theory, and I'll give you a taste of that later. As I said before, the Bayesian updating interpretation of the factorization formula, it's like Burke-Nash. It's the minimizer of Kullback-Leiter divergence.
That's what exactly. And so I'm asking, what does the
This is why I'm having these slides here. I want to convince you. Look, for example, one limitation of Burke-Nash equilibrium is that there is a language. It's not that easy to use as a guide for model building. I mean, it basically there is a representation of misspecified models, but it doesn't really tell you how to go about and write a model based on some intuition of people's misperceptions.
Are you saying that DAGs are natural restrictions?
There are natural restrictions that in many cases will give you an idea of how to incorporate a certain bias or attribution error in a model. And that's what the next 4 slides are trying to convince you. It's something that I think is, it's a special case, but a special case that can be motivated when you want to write down a model. Here are a few examples. So one example is that, for example, suppose that this is the true data generating process. That's just like the director's dilemma. The true data generating process is factorized like this, so it's consistent with this causal structure. And here is an example of a misperception. You just omit the link from 1 to 2. So you realize that 2 is caused by 0, but actually 2 is also caused by 1. So you don't take into account the effect of 1 on 2. So that's an example of coarse reasoning. So you can capture coarse reasoning by omitting links. For example, the fundamental attribution fallacy. So for example, 0 could be my own behavior, and 2 could be the behavior of somebody who's, I don't know, we're queuing in a supermarket, and I look at how this person behaves, and I'm willing to think that my own behavior affects his behavior, but I'm ignoring the fact that his own behavior is situational, depends on some external features that are given by 1. So I'm not realizing that his behavior is also a consequence not just of my behavior, but like what he ate for breakfast. So that's the fundamental attribution fallacy. So you can capture the fundamental attribution fallacy by just cutting a link. We already saw reverse causality. You invert a link. So take the true model, invert a link, cut a link. This will capture some kind of misperception of the causal structure. Okay? Like coarse reasoning, reverse causality. Here's another example. Suppose that this is the true distribution. So 0 is the initial variable, and 1 and 2 are condition independent consequences of 0. And let's interpret 0 as some state of nature, and 1 and 2 are my move and some other person's move. So the true structure is that we both observe the state of nature, and we condition on that state of nature, but otherwise our behavior is independent. So it's independent conditional on the state of nature. But here's my subjective DAG. I realize that state of nature affects my own action, but I think that my opponent's behavior is caused by my action. So whatever correlation exists between my action and my opponent's behavior, in reality, it could exist because we're conditioning on the same external factor. But I interpret that correlation as a causal effect. This can be interpreted as capturing the illusion of control. What's the illusion of control? One way of interpreting that is thinking that any correlation between what you do and something else, it suggests that you actually affected that. So you can represent the illusion of control by taking the link into 2 and changing the origin from 0 to 1. So it's like reorienting a link. So again, that's the true model. This is the subjective model. How do the two differ? Just by taking a link and changing its origin. So taking the link and changing its origin can be a representation of a particular attribution error, an error of causal attribution. So again, I'm trying to demonstrate that this language of having a true DAG and a subjective DAG that relate to each other by a simple operation, like doing something to one of its links, can be insightful in terms of representing a psychological fallacy or bias. Here's a very famous, important example in economics. This is the true distribution consistent with this causal structure. And by the way, I deliberately didn't go over this formula and show you the DAG because I'm sure that most of you are like me. And it's much easier to grasp this thing than that thing. Right? Some of you are geniuses who look at this thing and say, yeah, of course I understand that. But if you're like me, this is much easier to understand than that. Which is why the graphical models are useful, because for many of us, maybe most of us, it's easier to think in terms of pictures. So you see what's going on here. 0 causes 2, 2 causes 3, but part of the correlation between 2 and 3 is due to confounding by 1. And if this is the subjective DAG, then this captures correlation, confounder neglect. And maybe the next lecture, or at the end of this lecture, I'll give you an application with this kind of misperception. It's neglecting that the fact that some of the correlation is not between 2 and 3 is not causal, but due to confounding, that they have a common cause. And those are the kind of mistakes that applied micro people, when they teach you introductory econometrics, this is like one of the main kind of mistakes that people make when they reason about everyday correlations and extract causal links, and they just forget that some of these correlations can be due to confounding. Yes?
Does it matter that all these variables are observable?
Very good question. For what I do today, every variable that enters your model is observable because you put it into your factorization formula. So now you could interpret this example as 1 is actually being latent and the decision maker not being aware of that latent variable because it's not observable and he doesn't think about that, so he just thinks about these things, and the reason he's omitting that variable is that it's not observable. Now if it's not observable but he's aware that it is a problem, then we're starting to get into the problem of causal inference, that you're aware of this problem, but then how do you draw causal inference? So this will take us away from just the mistakes being causal perceptions that are wrong to mistakes of causal inference. That maybe your perception is correct, but the way you extract causal lessons from correlations might be wrong. Not today.
I think it just answers part of my question, but this is because we're in the behavior realm, we can do that, because if we're, at least in the context of econometrics, we always use DAGs as the experimenter, where we know if we have or not, and if we omit a variable and we create omit a variable bias, that's on the experiment.
So I agree, there is an interpretational ambiguity here. Here I'm saying maybe those variables are observable, maybe they're not, and for whatever reason, this is the DAG that the decision maker is working with. Maybe he's just not aware of one, maybe he's aware of one but doesn't realize that he should be aware of that, maybe he can't observe it, maybe he cannot observe it. I'm being agnostic about that. I'm saying for whatever reason, this is the DAG that he works with. So this captures neglecting of confounders, which is again a common mistake that economists talk about when they make fun of other people who reason wrongly about correlations and causation. Finally, the last example I want to show you, again, you could come up with other examples, is thinking about multiple causal channels. So suppose that 1 causes 3 through multiple causal channels, but the decision maker is unaware of some of them. Again, a common mistake that economists rail against, for example, you take a policy and you think about some effects, but you ignore some what we call second order effects, or how other people will respond to your policy. You just ignore that. That could be captured with this kind of DAG, that there's this salient causal channel, and there is another causal channel that is not salient. The economist, of course, understands in his wisdom that there is this causal channel, but the layperson doesn't understand that, so he neglects that and interprets everything in terms of this causal channel. So that would be another example of a simple common mistake that economists talk about all the time, and you can present that using the DAG language and interpret that as a mistake of causal perception. The purpose of those slides were to show you that you can take this DAG formalism. For now, we're not in a decision context yet, it's just representation of mistakes. And just trying to convince you that this idea of having a true causal model and a subjective causal model that relate to each other by a simple operation on the nodes and the links can very often capture interpretable mistakes, systematic mistakes that people make. Some of those mistakes were not initially formulated as errors of causal perception, but you can see that there are fundamentally mistakes of causal perception because you can represent it that way. That was the point of this slide, the representation. And now coming back to the confusion that we talked about before. Just the fact that you have a different DAG from the true DAG doesn't mean that you're going to make a mistake. There is an equivalence relation over DAGs that is, It's not exactly the same equivalence relation that you'll find in the textbooks. It's like there's a subtle difference, but it doesn't matter. But we'll say that R and Q, two DAGs, are equivalent, or I should say perhaps observationally equivalent, when they're mapping the P sub R and the P sub Q are the same. So you could have two different DAGs that are equivalent in terms of their distortion. And the simplest example is exactly what Tomasz said before. These two DAGs, one causes 2 and 2 causes 1, are equivalent because if I factorize P according to this DAG, this is what I get. And if I factorize P according to this DAG, this is what I get. But of course, we know that these two things are the same just by the basic law of conditional probability. Okay? So it just means, like Tomasz said before, that observation doesn't imply causation. In other words, observation equivalence and causal equivalence are not the same thing. So if we just view the DAG as a representation of conditional dependence properties, we should expect redundancies. And understanding those redundancies is helpful in calculations. And here's a famous result in this literature. Two DAGs are equivalent in this sense if and only if they have the two things. First, they need to have the same undirected version. So if you just look at the DAGs and forget about the direction of the links, they need to be the same. And now, if you do look at the direction of the links, then you need to look at the set of what they call in the literature immoralities. Immoralities are unmarried parents. So it's a technical term in the literature. So if you have a triple of nodes where you have I and J being parents of a common child K, but there is no direct link between those two nodes, it's an immorality. So look at the DAG and you identify the set of immoralities. So the two DAGs will be equivalent if they have the same non-directed version and the same set of immoralities. And if they're not equivalent, it means that there will be some P for which they spit out different distortions. Okay. So for example, these two things are equivalent because there is no immorality here and there is no immorality here. And they obviously look the same from a non-directed point of view. But these two DAGs are not equivalent because this one has an immorality and this one doesn't. Okay. So from an observational point of view, two DAGs can be equivalent. And again, we should understand that when we think about the DAGs as representing a misperception of conditional dependence properties, in some sense all we need is the equivalence class of the DAG. So you don't care about the DAG itself, you care about its equivalence class. And for many purposes, that's all you need. Once you integrate it in the decision model, you insist on a certain direction. You start insisting on a certain direction, you give meaning to the direction. But for many purposes, for most purposes if you like, all you care about is the equivalence class. So in this sense, you are not confused at all. You correctly perceived that all you care about about the DAGs is the equivalence relation. Yes?
I have a question. When you have a set of immoralities, then only play a role which elements are in this immorality, or also which elements are recurrent and which are charged?
The direction matters. So yeah. Absolutely. Okay, so now, so far I talked about representation. So what I'll do until the break, right? So the break is in 15 minutes. So what I'll do is just present the decision model, and then I'll start the next talk with what I thought would conclude the first lecture. Okay. For simplicity, I'm going to look at the case of an uninformed decision maker, somebody who doesn't see any signal before taking a decision. So I'm going to use X naught to denote the action. And this is where I'm avoiding those kind of confusions. I'm going to assume that 0 is an ancestral node not just in the true DAG, but also in the subjective DAG. In the true DAG, it makes sense. If I'm uninformed, what could possibly cause my behavior other than my information in the standard economic model? Now, in a non-standard economic model, maybe there are subliminal advertising messages that affect my behavior without me being aware of them. You could think about those things. And indeed, I thought about those things, but not today. Today, take a more conventional point of view, which says that the only thing that could affect my behavior is my information, because that's what I actively condition on. So if I'm uninformed, because I don't get a signal, then nothing causes my behavior, so my action is an ancestral node. And I'm going to assume that the agent understands that. He doesn't think that something causes his own behavior. That would definitely be confusing. That I think that something causes my behavior even though I don't condition on anything. That would be a bit weird. We could think about that, but not today. So I'm pushing these kind of potential confusions under the rug by assuming that 0 is going to be ancestral not just in the true DAG, but also in the subjective DAG. Okay? This is like the exogenous feature of the environment, the conditional probability of everything else given x naught, and that's exogenous and fixed. And so the only thing that is endogenous is the strategy of the decision maker, which is potentially a mixed strategy. That's how he mixes over x naught. That's the thing that is going to be the object of equilibrium. We're looking at expected utility maximization here. So these are the primitives. So subjective expected utility maximization means that, that if I'm going to take an action with positive probability, it should be a subjective maximizer. In other words, it should maximize this thing, which is exactly what you would do in a standard model, except that you wouldn't have this subscript R, so that's the only difference. And again, this is where you take a causal interpretation. This is, I think, the best answer that I can give. It's just a conditional probability, but it's a conditional probability that because we integrate that into a decision model, we give it a causal meaning. When we write this down, it means, what do I think is going to be the outcome given my action? Okay, so we have a causal interpretation built into that, but there's nothing more interesting that I can say about that today. So this is the subjective expected utility maximization. But remember, we saw that this thing is not well defined unless we know what the marginal over x1 is, typically. It could be sensitive to the marginal over x naught, which suggests, again, that an appropriate method for analyzing behavior here is an equilibrium approach. And this will be my definition of equilibrium. I start with a perturbed version. Now I want to be precise. So I'm going to, because there are all these conditioning going on, I want to make sure that I'm not conditioning on 0 probability events. So a strategy with full support is going to be a personal epsilon equilibrium. If every action that is played with probability greater than epsilon is a subjective expected utility maximizer. And then equilibrium is just going to be a limit of epsilon equilibrium. This epsilon equilibrium thing, in the case of an uninformed decision maker, is just to make things well defined. It doesn't play any interesting role. The trembles are not important. In the version with an informed decision maker, the trembles could be relevant for the set of equilibria, but here it really is just to make things well defined. It's not important. So for today, it's not really not important. So this is my equilibrium concept. Really, the only thing that is new here is this P sub R. Otherwise, this looks completely standard. You just maximize your expected utility. If you take an action with positive probability, it must be a maximizer. That's it. And again, no time to explain that at length, but this is actually a special case of Burke-Nash. This is a special case of Burke-Nash equilibrium. And as Jakub suggested before, this P sub R can be interpreted as the belief that minimizes Kullback-Leibler divergence from the true distribution, given the set of distributions that the misspecified model assumes. So that's... actually, I do have some time to talk about this example, so I'm going to do that. I have 10 minutes. So that's going to be my second example. Spirit's demand for education. As you'll see, this talk is going to be obsessed with useless actions that people take, even though they don't have, those actions have no consequences. So it's the second, but it's not the last time where we're going to have such an example of completely useless actions being taken. So this is the true process, and here's the story. The decision maker is a parent. The parent has a child. The action is the level of investment in the child's education. This is going to be a number between 0 and 1. How much do I invest in my child's education? Following the obnoxious terminology in the labor economics literature, I'm going to call theta the ability of the child. So theta is going to be the innate ability. 1 is going to be high ability, 0 is going to be low ability. S is binary. Actually, all the variables are binary except for A. A is a continuous variable. All the other variables are binary. S is the child's performance at school. Again, 1 is success, 0 is failure. And W is the child's subsequent performance in the labor market, like his earning later in life. 1 is success and 0 is failure. So that's the true process. The true process is that my investment in the child's education and his latent ability affect his school performance, but the only thing that affects his subsequent labor market outcome is his innate ability. School performance has nothing to do with labor market outcome. In the paper, I wasn't so drastic. I also allowed for a link from S to W. So really this, I'm not trying to claim that going to school is useless. It's just for the sake of this example, just to make things simple.
This is essentially the Spence signaling model.
Yes, but without the equilibrium signaling. Without the equilibrium signaling, yes. Again, being very cynical about education, the parent doesn't care about school performance per se, just cares about A and W. And the subjective DAG is going to mistake this correlation between S and W, which is in reality is due to confounding through theta, the ability. So in reality, the only reason that S and W are potentially correlated is because they're both driven by ability, but the parent ignores that. He thinks that the correlation is entirely causal. So he misinterprets the correlation, which is in fact due to confounding, interprets that as causal. This is again the type of thing that when you take an introductory econometrics course, they're kind of trying to drill this into your head that we make these kind of mistakes, but in reality at least it has some aspect of that, and the objective of the econometrician is to tease out the causal aspect from the observed correlations, which is why we use IVs, blah, blah, blah. But our decision maker is naive, he doesn't understand econometrics, so he views the correlation between S and W purely as causal. So that's the interpretation of this example. So that's the misperception, which is a special case of the confounder neglect example that I showed you before. This is the true process. This is the subjective process. You can see that the difference is that you omit theta and you reorient the link. So you remove a node and you reorient the link. That's the nature of the misspecification, or the graphical representation of the misspecification. Let's parameterize the problem so that I can show you a result. Delta is going to be the fraction of high ability children in the population. I'm going to assume that investments in schooling and ability are complements. So if your child has low ability, investment is going to be useless. But when your child has high ability, investment is going to be, the more you invest, the better the child will become at school. Of course, it's an assumption. You could argue that these things are substitutes, not complements. In the example, they're complements. Ability and investment are complements. And to make things as extreme as possible, I'm just assuming that W is just equal to theta. So high ability and leads to, deterministically leads to success in the labor market. Again, in the paper, it's more complicated, but I wanted to simplify things. This is the functional form for the utility function. You want your child to succeed in the labor market, and you don't like investing. So obviously, the only reason for you to invest is if you think it's going to be good for your child's education. For your child's subsequent earnings. And again, if you understood the true causal structure, you would realize that A has no causal effect on W, and that's why you wouldn't invest anything in your child's education. Okay? So that's the rational expectations benchmark. Nevertheless, under this subjective DAG, we're having a unique personal equilibrium where the parent plays an A double star that is greater than 0, so he does invest in his child's education, and that is going to be given by this equation. This equation is actually a marginal cost equals marginal benefit equation. On the left-hand side, we have the marginal cost of investing. Remember this utility function? That's the marginal cost of investing in the child's education is A. And on the right-hand side, we're having the perceived marginal benefit from investing in education. You can see the A double star here. That's the equilibrium aspect. So my perception of the marginal benefit of education depends on how other parents in the population perform, what do they do, and you can see that actually when A goes up, this thing goes down, and so the perceived marginal benefit goes up. So the more, so it's the opposite of what we saw in the Dieter's dilemma. Actually, I should have said that and I didn't. In the Dieter's dilemma, there was some kind of strategic substitutability. The more people consume the supplement, the lower my perceived benefit to consume this supplement is. I didn't emphasize that, but it was implicit in the calculations. Here we have complementarities. The more other parents invest, the greater my perceived marginal benefit is, and I'll explain that after the break. I think this is a good time to pause, some kind of a cliffhanger, trying to understand where this is coming from. But the point is that this is an equilibrium condition. This is an equilibrium condition where we see the equilibrium effect here on the right-hand side. We actually also see the direction of that equilibrium effect, that the more other parents in the population invest in the children's education, the greater my perceived benefit from investing in my child's education. Another thing, I'll take questions in a second. Another thing you can see from this is that when delta is very close to 0 or 1, there's going to be very little investment in education. So you're going to have investment in education being massive when there's a lot of variation in the ability of children in the population. Why is that? Everything here is driven by misunderstanding correlations. And if there is not a lot of variation in ability, there's not much that you can say about the correlation between S and W in the data. So there is going to be correlation between S and W in the data when there's variation in ability. So the only thing that could drive serious mistakes is when you have a lot of variation in children's ability. So this is a little bit like slightly degenerate because I have a binary distribution, but the insight is that if you had a huge variation in ability in the population, that creates scope for big misperception, big mistakes. But if there's a lot of homogeneity in ability in the population, that even though people make this kind of causal mistake, the implications of that will be relatively small. So that's like a general insight that you can get from this kind of model. Let's pause here, and after the break, I'll explain how this thing works, and then we'll move to the next subject. But I'm sorry, just there was one question.
This model doesn't capture one. It shouldn't make the understand fully the skeletal structure of the underlying causality web, but you must perceive the strength of some causality linkage, right? Like for example, if the true model education does have some effects, but the parents overestimate it, this model could capture that.
What you could do is do something that people do in many contexts, which is like model averaging. I mean, suppose that you thought that thought that with some probability, for example, you had some kind of doubts. This is not Bayesian, but this would be a natural kind of averaging, like Bayesian average model averaging, where you could say, I'm sorry, for example, I'm going to interpret the data as like a mixture of P sub r with respect to that and P sub r with respect to that, and so you will arrive at a belief that is some kind of a convex combination of these two things. It's a bit like partially cursed equilibrium, so sometimes partially cursed equilibrium can be interpreted in a similar way. I wrote a little bit about that, but that would be one way of capturing what you said. It's not Bayesian, so it's not like a Bayesian update from some prior. It's not. It's definitely not, but I think it captures what you have in mind to some extent. Yes? Yeah.
So you can assume somehow that the analyst, we understand perfect causal relationships as the decision maker completely wrong. This can come across as that we analysts are a little bit arrogant. Is there any more kind of democratic or symmetric way of setting up that both sides are confused, or we are confused, they are aren't, that would still make the model useful?
I don't know how to do that. I don't know.
Seems hard.
You would need to have some kind of it's like robust modeling where I haven't thought about that. Yes.
Yeah, my question was kind of related. At some point you said, okay, here I'm assuming that this informator has this specific tag in mind, but maybe with an equilibrium concept I can
you're absolutely right. If the only thing I care about is just representing the mistakes without integrating it in the decision model, then the only thing I care about is the equivalence partition. Once you integrate it in the decision model, I think it adds confusion because you sort of you really want to assume that that the action causes the signal. I mean, I see the signal and I take an action. From an outsider's perspective, it just sees the correlation between my action and my signal. Yeah, but do you really want to write down the decision model in which the signal is going to be a consequence of your action? It's a bit confusing.
No, I
So in the end, I think that I try to think about whether there are interesting questions that arise from this kind of confusion. I have a new paper where I partly address that, but I don't want to bore you with this new paper now. But for many purposes, I think it's just not an issue. Just take the causal interpretation of the DAG and just go with it, and don't worry about the conditional, about the equivalence relation. The equivalence relation will come in handy to simplify certain calculations. And just viewing it as a calculational device for, sometimes you look at the DAG and you say, wait a second, but now I can take an equivalent DAG, and that will simplify the calculation. Which effectively, that's what those algorithms do. They rely on certain kinds of equivalences to marginalize things and simplify the marginalizations. That's, for me, the most fruitful way of thinking about this equivalence relation as something that helps you calculate. That's it. And when you write down the decision model, just commit to the causal interpretation, because that's the one that actually makes sense and motivated the model to begin with. Yes?
So we have this representation results where many belief errors can be understood as causal misperceptions. Do we get additional implications or insights from this equivalent way of understanding belief errors?
Can you repeat that? I just didn't hear you.
So you basically show us that many attribution errors or belief errors, they can be understood or they're equivalent to having causal misperceptions.
Yes.
So what additional implications do we get from this?
I don't understand what you mean by additional implications.
For instance, do you have additional policy implications, say, if we want to mitigate certain imbalances?
So I think that in the end, for many purposes, those results will depend on the parametric structure. The DAG structure is non-parametric. There are going to be some properties that are going to be just a function of the true DAG and the subjective DAG independently of the parametrization. But to answer things like policy implications, you need to assume parametric things like, for example, is theta and A, are they complements or substitutes for school performance? So just having results to questions of this nature without assuming a parametric structure is overly ambitious. I will give you a sense of some questions. Some questions can be answered just by knowing the true and the subjective DAGs, but you shouldn't expect miracles. If you don't assume a parametric structure, you shouldn't expect answers that typically would respond to parametric assumptions. Should probably take a break now. Yeah, thank you.